This chapter goes pretty quickly because we did most of it in lab and we understand a lot of the concepts. I have the PowerPoint up and go through it, but there's a lot on this particular PowerPoint that I just skip right over because it's so basic and they kind of drag it out. And you'll understand what I mean as I go through it. First things first. Name the major types of blood vessels. All right, the big three, arteries, veins, and capillaries. Which way do arteries carry blood? Away, away. Which way do veins carry blood? Toward the heart. And what is the main function of capillaries? Exchange. Perfect. Okay, we're going to add to that knowledge. Look at the picture up here. As it gets bigger. I think you can follow that as arteries branch away from the heart, as they branch, they get smaller. Does that make sense? You have one big one that goes into a bunch of little ones and more little ones and more little ones. So further away from the heart, you get into more vessels, and they're smaller in diameter. Eventually, the arteries get so small that they get a new name. They call them arterioles. That may be new to some of you unless you've read the chapter. They're the small arteries, the smallest arteries. You'll even notice here that it's the arterioles that technically lead into the capillaries. And capillaries are always a bed of many vessels, not just one capillary. It's a group. We call them capillary beds. Then the capillaries collect and put their blood into little veins called venules. They're technically different than veins. Okay, venules and arterioles are a little different than small veins and small arteries. But basically, for our purposes, they function like small veins and small arteries. And then, as the blood flowed from the arteries into the capillaries, and it starts collecting in the veins, what happens to the size of veins as the blood gets closer to the heart? Oh, it's exactly opposite of arteries. Well, it's the same, but the blood's going the opposite direction. So the blood starts out in lots of tiny venules. As they collect, they get bigger. They go to small veins, and then they go to larger veins. And where's the largest vein? Right at the heart, that join the heart. And tell me, just from your knowledge that you already have, what are the two veins that attach to the heart? Yeah, superior and inferior vena cava. From lab, you already know the layers, so I'm not going to spend time going through it. If you need to brush up on it, you don't need to listen to the lecture here. You need to go back and listen to the other one. So know your layers, your tunicas, know what kind of tissue they're formed from. Any hollow tube could be called a lumen. We understand that. Here's the picture, and you would find it in the blood vessel lab, blood vessel lab part 1. Look here. Some arteries are elastic, and some have more muscle. Does it make sense to you that where that 120 pressure goes into the aorta, that it would need elastic tissue because it stretches? And when that blood moves on, what does that pulse area, that area that was stretched out, what does it do after the blood moves past? Good. It recoils. It snaps back. Just like fruit of the loom. Okay? Wash after wash. Pump after pump. Beat after beat. It snaps right back. Notice, we said nothing about contraction of the blood vessel. These blood vessels are not contracting back. It's not an act of muscle tissue. It's the elastic fibers that were stretched snapping back to their original size. Okay. Look, there you see an arteriole. Notice how it's a lot different. It's a lot thinner, and it doesn't actually have continuous thick layers of muscle. The muscle's kind of sparse. Not a big deal for our purposes. And there's a venule. It's like the venous component of an arteriole. I dig this one little part. We already saw, some of us saw the picture from, the lab a long time ago on blood, where I had the PowerPoint that had the red blood cells going through a capillary in a single file row. That's pretty cool. This is just a reminder of that. Notice, there are a few tissues in the body that don't have blood flow, so they're missing capillaries. We know that about cartilage. You learned in AMP1 that cartilage is avascular. Therefore, it cannot have capillaries. We learned that epithelium gets its nutrients and nutrition from the underlying connective tissue. So there's never a capillary within the epithelium either. And then your eye, your cornea and your lens don't have blood flow through them. They don't have capillaries because they're in a fluid environment. So they get nutrients from the underlying tissues as well, from the fluid. You remember studying aqueous humor and vitreous humor? The three types of capillaries I cover in the chapter that it's relevant to. I don't think that it makes a lot of sense for me to have you just memorize these and not talk about it for 4 more weeks and then bring it back up. So we'll only do these later. Fair enough? When we get to the liver, I'll talk about sinusoidal capillaries. When we get to the kidney and we do the glomerulus, I'll talk about fenestrated capillaries because then we'll see them. And it will make more sense when we do it like that. So then this stuff we don't have to really go through. In my mind, we cover it later. And it fits really well later. I do like this little tidbit. There's somewhere in the neighborhood of 10 to 100 vessels per capillary bed. And a nice concept. That reminds you that it's a capillary bed. I don't care that you know exactly how many. It's just a bed. It's not one capillary. It's a group. And capillaries branch from what vessels? Arterioles. Arterioles. So here's our capillary bed, right here. I'm going to zoom up even more on it because I really want you to see this. What's the red side called? Yeah, that's the arterial end. And here they're showing us arteriole, but it's just the arterial blood. Notice here, it's red on this side. Why? Yeah, when it's oxygenated, they like to show it in red. When we're systemic, that means out in the body, red is usually arteries. So when you see red, you can think arteriole as long as you're not in the lungs. Okay? As long as you're out in the body, that's okay to think of. Notice, as it flows across here, hey, wherever we have branches here, the first few branches, notice there's a round muscle there. Do you know what you call a round muscle? A sphincter. This is at the beginning of the capillaries. So it's called a precapillary sphincter. What could be the purpose of these precapillary sphincters? If you don't need blood in certain areas, you contract them and the blood does not go there. Watch this. If we contract them, the blood doesn't get in here, it just goes straight across. Are there times where you don't need blood flow to your digestive tract in as great an amount, right? When the sympathetic nervous system kicks in, this happens in your digestive tract. To divert blood flow or shunt, divert or shunt blood flow. Notice, why don't we need the sphincters on the back end over here? Because the blood's not going in. It would make no sense to put the sphincters back here. That would pinch it off and that would build up fluid here, dilate things and be bad. On the lab talk, we know that there's layers there. We can even zoom up on it. Wow. And that's an artery because it is holding its shape because of what tissue? The elastic tissue, the two layers that they sometimes call elastic membranes or elastic lamina. I love this pie chart. Because I'm hungry. So, you know, I don't do that many pie charts, to be honest with you. I didn't create this. Publishers don't create that many in AMP, so I don't do that many. This one's good because the very first thing on here, this big thing here, blows people's minds because almost nobody even concepts this. The average person thinks half your blood's in your arteries and half's in your veins. And that's what we think. Look here. And really most books say more than this. Most books say like 65 or 64. Typically. This book changed it on this edition. I don't know why. You know, it can vary. But anyway, the point is, over half of your blood, 60+% of your blood at any given moment is in your veins. Remember, the lumen of the veins is bigger, right? The wall is thin, so the space is larger. They hold more blood. How much more than arteries? Do you see that? That's what I really want you to own. Your veins hold about 4 times more blood than your arteries. And you know what? Depending on what book, it may be even more than 4 times. Some books it's closer to 5 times. It's a lot more. That's the key. 4 to 5 times more. I think this totally blows people away. There's almost as much blood in your lungs as there is in your whole arterial system. Does that blow you away? I mean, I wouldn't have concepted that before I was, you know, an AMP guy. I just didn't think of it like that. Look, there's more blood in your lungs than there is your heart. Well, I don't think that surprises anybody. But what might surprise you is almost 10% of your blood flow at any given moment is actually in your heart. Okay, now let me tell you how I ask things. I like you to know more, less, 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 less. I don't ask you the percentages. But what I do like are the relationships. 4 times more venous blood than arterial blood. I do like that. And know the order. Veins, arteries, lungs, heart, capillaries. That's the order. Because it just gives us a new concept of things. We think, wow, 4 times less blood in the arteries? How do we get blood to flow through veins? I like asking that because, you know, we listen to Integrity's ahead, we read ahead, we learn some things, and then I ask a question like that, and our brain goes to what we've learned and studied, not to what we know. If I asked any little kid on the street, what pushes blood through your veins, they would say, your heart. Never forget that's the number one answer. Everything you guys said was correct. But the number one answer is your heart pumps blood out. The pressure here is 120/80, right? I'll just show you. The pressure in a capillary, which I'm going to tell you again in a minute, on this side, I'm going to do it backwards. For me, this is the arterial end. You do not have to write this at all. This will show up in a picture in just a minute, and you can write it then. And on the venous end, it's about 17. Wow. And then when it gets in the big veins, it's about 8. And when it gets back to this atrium, it's 0. Virtually no pressure there. Look, we start out at 120, we end up with 0. That is the primary mechanism. Things move from high to low, don't they? So it moves towards the lower pressure, always pushing. But notice the small vein, the pressure's only 8. And to move it back to the vena cava, maybe it's 1 in the vena cava, 1 to 0 in the vena cava. That's not a lot of pressure. It's enough to push a little, but it's not a lot. So my question now is, what aids venous flow, or what helps venous flow? And that would be, here's a vein. What do veins have in them? Valves. See, without valves, nothing would help. So the key, the first key, is the valves. And here's why. If we were to squeeze this vessel right here, what would it do? It would push blood up through that one, and it would close this valve here if some blood tried to go down. Correct? It would have no choice but to go one way. Therefore, because there are valves in veins, anything that squeezes a vein tends to push flow through. Now, not a squeeze that cuts off, but a rhythmic squeeze, or a squeeze and a let up. So, all movement pumps blood through your veins. Every time you move, the muscles squeeze your veins, and they help to push a little extra blood back. You ever heard that exercise is good for your circulation, Josh? Why, sure. Okay. Hey, when you lift weights, what happens to the size of your veins? They get bigger. They get dilated a little bit. What else, other than movement and blood and muscular contractions, what else could squeeze on a vein? Arteries pulse. And they lay either on top of or under a vein. So when that pulse rolls through the artery, it bulges right into the vein. Arterial pulsation. And there's a third. Breathing pressurizes your abdominal and thoracic cavities. Whichever one is getting pressurized, it squeezes the vein a little bit and helps to push the blood. That doesn't help in your arms and your legs. You're not breathing in there, right? It doesn't help in your brain, but it helps in your torso. So we can say respiration. Or breathing. You don't have to say respiration. You can say breathing. Totally cool with that. These three work only because veins have valves. Without the valves, that would not work. What do you call it when a vein gets stretched out so much that its valve doesn't meet in the center? That's what a varicose vein is. It's a distended vein. The valves no longer meet, therefore it can fill up with blood. What kind of things cause varicose veins? It's all about one word. It's all about pressure. Pregnant women commonly get hemorrhoids. Why? The baby is pressure. Okay? It's pressure. It pressurizes it down there because they get the excess baby pushing down, the excess weight pushing down that their body's not used to. People that have jobs where they stand in one position a lot without moving get varicose veins because they pressurize their legs. So they tell you to alternate your leg, put one up, put one down, move a little, don't lock your knees out, stuff like that. Varicose veins can be tiny veins like spider veins, or they can be bigger around than my pinky. It just depends. The word anastomosis with an I would be singular, with the E at the end, ES, is plural. This means an interconnection between blood vessels. It's really like an alternate path. Imagine this. Imagine you had one blood vessel that went to a certain area, and you clog up that one blood vessel. Then all the tissue would die. But if you have alternate pathways to get there, then if the one gets clogged, the other ones can take over. So anastomoses, or interconnections, provide collateral, this word, flow, or collateral channels, alternate pathways for blood. That's a protective mechanism. Do you know some people's hearts, when they get plaquing or they get blood vessels that aren't working, sometimes they grow new vessels that can bridge the gap. Doesn't always work to save everybody, but some people's bodies do some amazing things. All right, blood flow. Do I really have to tell you what blood flow is? But look at that technical definition. This is how school is. I say something like blood flow, and you're prepared to write that definition down. Because, we just got to nail it. We got to know it exactly. You got to know that definition exactly. You got to know that blood flow means the fluid, the stuff that's in your blood vessels that's moving. However, when they measure blood flow, they usually measure an amount over a certain time period. Okay? Like cardiac output, liters per minute, or milliliters per minute. That's how they do it. Blood pressure. It's kind of the same, right? We can define it. Force per unit area exerted on the wall of a blood vessel by the blood. Oh no, let's understand it instead of writing that. If you have fluid in a tube, the fluid pushes in every direction, doesn't it? It tries to push out here, it tries to push out here. Of course, when it's flowing, it's moving more in one direction, but that fluid would still be pushing against the edge of that vessel, wouldn't it, on the sides? And that is pressure. Just like a balloon. It is this bullet right here. It's that pressure gradient that keeps blood moving. That's what pumps blood. The number one fact that pumps blood is the pressure created by the heart and the vessel. And I think that's just pretty logical. Now we get to a word that may be new for you. And when we're talking about blood flow, we need to talk about resistance. Resistance is anything that works against the flow, that makes it more difficult for the flow to happen. The three most important facts or physiological things that lead to resistance are these right here. So before you try to memorize them all, let's think for a second. If blood is flowing and the blood gets thicker, will it flow as easily? No. If we put motor oil in we just opened you up and started pumping motor oil in and blood out, would your heart like that? No, it wouldn't pump it as well. I mean, obviously your tissues wouldn't either, but that's not the point. The point is, the thicker the fluid, the harder it is to move. What's the number one factor that relates to viscosity of blood? The amount of red blood cells. Very good. Very good. The amount of red blood cells, remember, blood is 55 plasma, 45% formed elements. Majority of those are red blood cells. Primary factor is your thickness of blood has to do with red blood cell count. Okay, blood vessel length. The longer the blood vessel, the more resistance because there's friction up against the side of the wall. I don't talk about that one much, but that's how it is. This one I totally need you to own. Is it more difficult for fluid to flow through a little vessel or a big vessel? Okay, so here's how to think of it. And notice my inflection was a little off on that because I wanted you to wonder. I wanted you to say the answer and then go, was I right? He's not saying anything. Well, I don't know. And that's why it's this simple. If the vessel is small, you're going to have a hard time pushing more stuff in there, aren't you? So that's going to be greater resistance. There is more resistance on small blood vessels. The area of the most resistance in your entire cardiovascular network are those little new vessels we just learned called arterioles. The majority of the resistance occurs within the arterioles. Okay, this word right here. I've probably said it in the lab, but I want to mention it again, just make sure everybody hears it. Laminar flow is normal, smooth flow through a vessel. Laminar flow, smooth flow, makes no sound. If you were to take a stethoscope right now, put it in your ears with the pieces facing forward, take the bell or diaphragm and put it over a blood vessel and listen, 99% of the time you're going to hear nothing. Because smooth flow through a vessel makes no sound. That's why when you check somebody's blood pressure, before you pump the cup up, if you listen, you don't hear anything. Because it's smooth flow. Right? Makes no sound. Why? Because it's moving right down the middle of the blood vessel, nice and neat and easy. However, if something constricts a vessel, narrows it abnormally in one area, as the blood goes through, it's going to whoosh and swirl, just like stenosis in the heart valve. Okay? If you get a narrowing or if you get turbulence in a blood vessel, it will make a sound. And any sound, okay, an abnormal sound in a blood vessel is called, do you know how to say the word? Bruit. Does not look like brewy, does it? You do not pronounce the T. So think brewery and leave out the and then you'll say it right. Brewy. What is a brewy? Yep, it's a vascular sound. It's an abnormal sound in a blood vessel due to turbulence. Do you think plaquing in blood vessels could cause that? Absolutely. When you go to the doctor, if you have high blood pressure, if you have heart problems at all, they will listen to your neck. They're checking for that to see if your carotids are plaqued. You can detect it sometimes that way. They would also probably do an echo of your carotids and of your heart and things as well. What's an echo? It's an ultrasound of your heart. It is. Or, yeah, we got to put cardiogram, right? Yeah. How many people are going to go to sonography school? Cool. It's way cool. Oh boy, look at this. Now we get the deltas, and we get the formulas, and we get the freaking out. Let's not do that. Let's be very logical here. There is a math term, oh, I said the M word. There is a math term that you need to understand. What does inversely proportional mean? An opposite relationship. If one goes up, the other goes down. It's not telling us how much, even though there is a formula for that we don't care anything about. All right? And here's the deal. Flow is opposite to the resistance. If the resistance goes up, the flow goes down. I don't know, does that make sense? If you make it harder to move, it's going to slow it down? That just makes sense. When flow is opposed by resistance, we get pressure. Okay, I can comprehend that. Let's look at this. Ooh, I made it too big. This one's so important that I'm going to make it big screen for you. This is another graph that is exceptional in teaching some things that we may understand but may not be able to see yet. And this is the first thing. Every single one of us knows right now, normal blood pressure as we are measuring it is 120 over 80. The top number, systolic, is when the heart does what? Squeezes the blood out, right? Makes the pulsing, and even though the blood vessel gets bigger, the pressure still goes up because there's excess blood in there, enough to drive the pressure up. Look, that's the 120 number. right here. The 80 is when the ventricle relaxes and the pressure drops. So in your big arteries, your pressure never hits 0, right? It doesn't even get close to it. The lowest it gets is around 80. Hey, I know some of y'all have 110/70 pressure or 90/60. In your case, that's where this would be. But we're doing average right here. So look, in the aorta, pressure is 120/80. Even in the big arteries, it's 120/80, and then it starts to drop a little as we get lots and lots and lots of branches. But when we measure it in the brachial artery, it's still right in this range. It's still the big arteries. Now look, this is what's so cool. As blood hits the arterioles, that means it's gone through those arteries. It's gotten far enough away from the heart that when the heart contracts, it's barely pulsing. Do you see that right here? This is the pulse pressure, isn't it? The difference between the contracting and relaxing pressure. That's the pressure that created a pulse. As you get further and further from the heart, the pressures get closer together. And eventually, when you get far enough away, the flow just gets smooth. There's no longer surges. There's no longer pressure surges. Tell me, in what vessels is the pulse lost? Now, I really want you to say arterioles. Come on, mouse. Right here, where it comes together, I know it's still a little thick. We're going to say the pulse is lost. It's no longer detectable in the arterioles. I am going to associate a few numbers with this graph. If you have it printed out, great, you can write right on it. If you don't, that's okay too, you can write the words. Hey, look, in the aorta, to the small arteries, the pressure drops a little, but look, from here from 120 maybe to 90, right there. Okay, not such a huge drop. But look here. When we hit the beginning stage of the arteriole, the pressure can be as high as 90. And what is it when it leaves here? What do you think? That's 40, that's 20, so this is 30, so that's about 35. By the way, what number, while ago, did I tell you when blood enters the capillaries, the pressure is at? 35. There's your number right there. The beginning capillary pressure is 35. That's the same as saying the ending arterial pressure, isn't it? It goes from arterioles to capillaries. Tell me, how much of a drop occurred during the arteriole range? Wow. If this is 35 and that's 90, that's almost 3 times. Not quite. That's a lot. That's significant. Look here. In the capillaries, it drops from 35 to what did we say? Look, there's 20, there's 10, there's 15. Oh, we're saying 17. So it's cut in half in the capillaries from 35 to 17. But in the arterioles, it goes from 90-something to 35. The most dramatic decrease in pressure occurs in which vessels? The arterioles. The arterioles have the greatest decrease in pressure, and they also are where the pulse is lost. And we'll see something else in a minute. Okay, venules, I don't get big on venules, but look at the veins. Remember we said earlier, venous pressure starts at about 8. And in the vena cava, it's virtually none, 1 or less. And by the time it hits the heart, it's roughly 0. Hardly any pressure there. Wow. When you do lymphatic, when you listen to the lymphatic lecture, and when we do lymphatics in lab, I'm going to tell you that lymphatic fluid is tissue fluid that's out in the body that gets collected by a special circulation. And that special circulation will filter it and send it back to the blood. Do you think it would try to open up, this little low pressure system would open up into an artery, into an arteriole, to a capillary, a venule, a vein? It's going to open up somewhere where the pressure is teeny tiny low, really close to the heart, because that's where the pressure is lowest. Okay? That's a concept that we'll learn later. Wanted to introduce it now so you would know when we get there and when we say what the answer is, it'll stick with you because you're like, oh, that makes sense. You would open up into low pressure. All right, so that's this graph. Explains a lot of stuff. Pulse pressure, right there. We already did that. We did this stuff earlier. We know about capillaries. We know about the venous pump. Look, there's a picture showing a muscle squeezing a vein and forcing blood through an open valve, actually opening the valve and closing the one on the other side. Love it. Oh my goodness. Blood pressure, you need a heart and blood vessels and kidneys. And yeah, the brain does something with it. We already looked at these things. We know what blood volume is, resistance, and cardiac output. Oh, we don't need to get totally crazy on that, do we? Okay, we won't. And that flashes me back to, see, what happens here is they start repeating stuff from the heart because now they're talking about what the heart feeds the blood vessels. So there's all this duplicate stuff that we've already learned. I need to tell you what end diastolic and end systolic volume are because I didn't do that when I did preload. Our heart's getting tired. It's twisting up. It's going backwards. It's sad. Oh my goodness. Name this valve. Excellent. Pulmonary semilunar. Name this valve. Aortic semilunar. Do they have chordae tendineae? Chordae tendineae? No, we don't have any cords going up into those blood vessels, do we? They're just little flap valves, just like the valves in the veins, by the way. Venous valves are semilunar valves. They're the same. These valves, however, the AVs do. We're not so concerned with that right now. Let's look at this little chamber right here. When it is full of this stuff called blood, right here, we know that there's so much of it. An average heart full, 120 milliliters. I'll just put that there for you. When it's empty, it's not empty. But when it's empty, on average, there's about 50 milliliters in the heart. So how much left? And what do we call this? How much left in one beat is called your stroke volume. Full minus empty equals stroke volume. Two terms, end diastolic volume and end systolic volume. So you got to know what diastolic means and systolic. Let's do this one first. What is systolic? Contraction. At the end of contraction, the chamber is at the end of contraction, the chamber is empty. Not really, but it's as empty as it's going to get. True? So end systolic volume is the empty chamber. Okay? After systole, the chamber is empty. I mean, it means right after. Does that make sense? At the end of contraction, the chamber is empty. Tell me about the chamber at the end of relaxation. Right. When the ventricle relaxes, that's when the atria fill it up. So end diastolic volume, end relaxing volume, is when it's full. Which one of these two terms, end systolic or end diastolic, would relate to preload? Good. A full chamber stretches, right, is stretched. And that stretch that preloads the chamber determines how hard it contracts. End diastolic volume relates to preload. Wow. Then you get stuff like this that you need to look at on your own. because it takes time to think through. Control of blood pressure. Would you believe that the nervous system and hormones can both control blood pressure? I'm just guessing you would believe that. Sympathetic and parasympathetic, epinephrine, norepinephrine. And you guys need to understand that your hormones in your nervous system are short-term regulators. Your long-term regulator is the blood volume, which is produced by the kidneys. So long-term blood pressure is actually regulated by the kidneys, renal, which you see right here. So then it goes into particulars of it. And where we want to get is right here. There are structures called baroreceptors. You know what a barometer measures? Pressure. It measures pressure. Baro means pressure. Baroreceptors are located in your aorta and your carotids. What kind of vessels are those? Arteries. They are stretch receptors. When the BP is up, it pushes against the wall of the blood vessel and creates stretch. This is negative feedback that wants to lower the blood pressure. So tell me two things that could happen to lower the blood pressure. Decrease heart rate and dilating blood vessels. Does that make sense? If the blood vessel is stretched and then we relax the vessel a bit so it opens up, that would drop the pressure. The nervous system controls this. See, it's your medulla and your pons, your brain stem. Your brain stem has centers for this. So the baroreceptors fire when we have stretch from the blood pressure. It goes into the brain. The brain sends signals out that would try to lower the blood pressure. This only works short term. If you have chronic high blood pressure, this mechanism gives up. It's a short-term regulator of blood pressure. Baroreceptors. See how many slides they take to say the same thing we just did? That's kind of cool, though, because it means, man, we're learning a lot in a real short amount of time. There are also chemoreceptors in the same place. Chemo. Who wants to be bold enough to tell me what chemo might relate to? Why, maybe they measure chemical concentrations. Do you think that this is important? What is that? Oxygen. Do you think that this is important? Yes. Do you think this is important? pH. What's pH a measurement of? Good acidity or hydrogen ion concentration. This is the order I like to have them written in. I know I hopped all around and you didn't see this till the end. Here's your slide. If you don't want to write it down, you don't have to because it's right here. Okay? But watch this. When I teach chemoreceptors, since we're talking about oxygen, I relate it to breathing because we understand a very important concept that so goes the heart, so should go respiratory. Correct? Because sympathetics speed them both up, don't they? So we know this. So check this out for a second. If we have elevated CO2, and by the way, your blood can only carry so many chemicals at one time. When we get to respiratory, we'll talk about how if it's carrying more CO2, it has less oxygen, and if it has more oxygen, it's carrying less CO2. So these are going to be opposites. And you may remember this. I promised you, and I hate to break promises, that formula would be very important. Okay? So before I go back up here, here's what I'm going to say. If in our blood we have more carbon dioxide, it automatically drives the reaction this way, and we end up with more of these. What does that mean? Look up there for a second. Remember, pH is an inverse log. Okay? The more hydrogen ions you have, the more acidic it is, but that is a low number on the pH scale. So, how do we want to do this? Maybe instead of putting pH, I should put hydrogen ion concentration right there. And which way? I didn't have to erase that. You don't have to erase it. My 2 was too close to the H, and it made it look like CO2 goes up. What's it do to hydrogen ion concentration? It's up. And that is a low pH. The easiest way to learn this is to start with oxygen. If you have low oxygen, your body's going to want to do more what? Increase breathing. Do you agree with this? Okay? Hold your breath, develop low oxygen, and see what you want to do. Okay? You know that already. If you hold your breath, you're not only using your oxygen, you're building up your carbon dioxide. I don't know if you know that. Your cells make carbon dioxide when they're making ATP. So when you hold your breath, your CO2 goes up. As your CO2 goes up, it makes you want to breathe. See, when you're doing a little contest with your nephew or niece in the swimming pool, who can hold their breath the longest? You cheat. Underwater, you blow the air out slowly. If you really try to hold your breath, your CO2 builds up faster. But if you blow the air out slowly, it lets your CO2 levels drop. CO2 is the number one chemical for causing you to breathe. It is not oxygen. We didn't know that. We're taught it's all about oxygen. It's really mostly about CO2. That's what's crazy. CO2 drives all our breathing, realistically. Enough of that. Here's what we use. If it causes you to breathe more, what does it do to your heart rate? We know they go hand in hand. So look, all of these things would increase the heart rate. Why? To pump more CO2 out. And to give us the opportunity to pull more O2 in. So let's go back here. These are more important in regulation of the respiratory rate. Would you agree with that statement, even right now? I would. Okay, hormones. Wow. And remember what we're doing here. We're doing all about blood pressure. If your heart rate goes up, what happens to the blood pressure? If all other factors stay the same, it would go up. If all other factors stay the same, it would go up. Okay, hormones. Any surprise to you that norepinephrine and epinephrine can increase cardiac output? Shouldn't be, but here's the other part you need to know. They are good vasoconstrictors. Okay, instead of memorizing that, understand. If your blood pressure goes up, it goes up because your heart's pumping more or because your blood vessels got smaller. Both of those two facts raise blood pressure, so those always go hand in hand. And there's this chemical that we'll talk about later. Angiotensin II that causes vasoconstriction as well. Don't worry, you'll own that one later from what we have to talk about. ANH and ADH and aldosterone. Anything to do with this? Lower blood volume, lower blood pressure. Increased urinary volume, all that good stuff. We have all that. Okay, long-term blood pressure regulators. Well, see, the baroreceptors are quick to adapt, so that long-term they're not of use. What is of use is the kidneys. And there are two mechanisms, the direct and indirect, which sounds crazy right now, so just go to the next slide with me right here. What do the kidneys do? They filter the blood. Let me ask you a question. When they take fluid out of the blood, where do they put it? In the PP. Do you agree? They take fluid out of the blood and they turn it into pee. That's what your kidneys do. That is directly what your kidneys do. So, if we increase the volume of blood and increase the pressure, the kidneys filter more and lower the pressure. That sounds like great negative feedback. That sounds like a very direct function of the kidneys to help regulate blood pressure. When it goes up, more gets pushed out. It's that simple. And the opposite is the opposite. That's just what the kidneys do. If you have high blood pressure, they filter more. Have you ever heard high blood pressure is really bad on the kidneys? That's why. It stresses the vessels. It causes them to rupture early. That's kidney damage. Oh boy. This is the big one right here. Main, major, primary, super important regulator of blood pressure. Long term. Bless you. This is called the renin-angiotensin mechanism. You will completely understand what that means in a little bit. And I like to draw it instead of just letting you write the bullet. What mechanism? Renin-angiotensin. Is it the direct or the not direct one? It's indirect because it uses chemicals. When you have, is there an easier way to write this? How about that? When you have low blood pressure, believe it or not, I remember learning this, thought it was so cool. The kidneys monitor your blood pressure. Not only that, they monitor the chemical concentration of the blood too. But we're sticking with pressure right now. So as the kidneys monitor the pressure, by the way, what organ's monitoring the pressure? Kidneys. Does the heart monitor it too with little stretch receptors called baroreceptors? Yeah, that's short term. Okay, this is long term. When the pressure's low, the kidney has a group of cells that release a chemical called renin. Well, we can call this an enzyme. We can kind of call it a hormone because it travels through the blood. So what they do is sometimes they call it an enzyme, sometimes they call it a hormone, sometimes they call it an enzymatic hormone. I don't care where it fits in. Here's what we need to know. What's that? Okay, sure, I made it a capillary, but now I'm just telling you it's a blood vessel right now. In the blood, we now have renin. It's dumped into the blood. Okay? Are there many, that's renin, I just wrote renin in there. Are there a lot of chemicals that are naturally there in the blood? Are there these things called plasma proteins, many of which are inactive, that we've never even heard of? Yes. And one of those is called angiotensinogen. It is an IBP, angiotensinogen. Oh, my people who love language, name Alexis. What do you think angio means? Angiography? Angiogram? Anybody? Blood vessel. How about tension? Tense. The tension. Okay? On a blood vessel. That's what that refers to. Blood vessel tension. Might that have something to do with the pressure in the vessel? Are we monitoring blood pressure right now? When the blood pressure's low, the kidney detects that. It dumps a chemical called renin in the blood. Renin is an enzyme that turns this into, take a wild guess what that is. AT1. What could AT stand for? Look, you drop the ogen off, right? Ogen's an inactive word. We drop it off, it becomes angiotensin 1. Where is angiotensin 1 located? Good answer. In the blood. Oh, that's cool. Why not? We'll narrow it down. Probably shouldn't have done that. No, that's okay. Actually, that's very logical. In the blood. Where does your blood go? Oh, endocrine people. Everywhere you have blood vessels. Eventually, does it pass through a set of little jewels that you have that look like this? That has a little happy little heart between them? What are these things supposed to be? I know, look, that lung's taking a bite out of the heart right there, or the heart took a bite out of the lung. Anyway, you'll understand that later on. Yes, there's your bronchial tree. Now you know those are the lungs. Quite ugly. Hope none of y'all's look like that. But anyway, the lungs, this is cool. They make a chemical, and they dump it into the blood. And it is called, yes, it was hard converting from doctor writing to teacher writing the first year that I taught. Because you have to be able to read what I write. Oh my goodness. Low blood pressure causes the kidney to dump renin. Renin goes into the blood. It is an enzyme that acts upon an inactive blood protein. That means it's always there, right? Called angiotensinogen. It turns it into angiotensin 1. Angiotensin 1 is coursing through the blood. When it gets into the blood vessels in the lungs dump this chemical called ACE, angiotensin converting enzyme, in there, and it turns AT1 into angiotensin, anybody want to guess? 2. I know I'm supposed to use the Roman numerals, but it's easier to read that way. Angiotensin 2 stays in the blood. It's in the blood. And it causes, look how I did this, vasoconstriction. Oh, that's cool. When the blood vessel gets narrower, what happens to the pressure in the vessel? It just went up. See, the kidneys make a chemical that eventually causes blood vessels to be constricted. But only when the lungs are working right. Who would have thought your lungs played a major role in long-term regulation of blood pressure? They make a hormone, an enzyme. An enzymatic hormone, we could say, because it also goes in the blood and acts upon stuff. Have you ever heard of ACE inhibitors for blood pressure? That's what they inhibit, angiotensin-converting enzyme. That would lead to dilation, which would help to lower the blood pressure, which is the exact opposite of this. Anyway, you need to understand this. The other thing is, this is what's cool, angiotensin 2 stimulates ADH and aldosterone to be released. Angiotensin II. Not only is it a vasoconstrictor, but it causes ADH and aldosterone to be released. Wow. What do ADH and aldosterone do? Increase blood volume and increase blood pressure. Right on. And maybe just a tad bit of vasoconstriction by the one that's called vasopressin, ADH. Do you see how that fits all together? Would you have liked to have tried to learn this before we did hormones? No way. You see why they teach things in the order that they teach them? If we tried to do cardio without already knowing hormones, we would have had to learn half of the hormones just to understand cardio. It would have been crazy. This simple squamous epithelium, why is it simple squamous epithelium? Right, to allow stuff to move. Do you guys already know, which you should know, but on this side of a capillary, this is the arterial end. The artery is attached on this side, arterioles. And this is the venous end. It leads to the veins. We're doing one capillary, not a whole bed. But on this side, stuff moves out, fluid moves out, and on this side, it moves back in. How many of y'all knew that already? No? Okay, so now you know. On a capillary, on the front side of the capillary, it's moving out, fluid's moving out. Remember, the pressure started at 35 millimeters of mercury, and by the time it ends on this side, what was it? 17. You remember that pressure flow chart that I showed you? That's 17. I'm squiggling the millimeters of mercury because I was just trying to fit it in there. 35 to 17. In less than a millimeter, the pressure drops from 35 to 17. What would be the main reason the pressure would drop? What would you think? Well, we just lost fluid. We lost more than goes back. So the pressure, that drops the pressure. As fluid falls out, the pressure drops. That's just one force. There are actually 3 more forces that we're going to mention. Keep in mind when we talk about this, that there are actually 4 forces that determine movement out, and those same 4 on this side determine movement in. Now, I like doing this because it really is a lot easier than it sounds. We throw fancy words on here and it sounds tough, but look, we have a fluid in here. What's the fluid called? Blood. Everybody agree? Isn't there a fluid outside of this blood vessel too? We're going to call it interstitial fluid. It's different. It's pretty different than that. Similar, but different. Way less protein. It's similar without protein. Let me just ask you a question here. Does the blood have any pressure? Yes. Which way is the blood's pressure pushing? And don't draw this yet, but just look. Out. Does the fluid have any pressure? Which way do you think it's pushing? Oh, please don't write it yet. I want you to see it before we put it on paper. In. Are there any solutes in here? And they would be doing what? Sucking in. Are there any solutes here? And they would be sucking out. Look, 1, 2, 3, 4 forces we just mentioned. 2 of the forces are related to the capillary, and 2 of the forces are related to the interstitial fluid, which they don't put ISF, they just put IF. So you'll see a C and an IF for a capillary force versus an interstitial fluid force. Okay? You're going to have 2 C's. You're going to have what's called a HPC, and then you're going to have an OP. And then you're going to have a HPIF and you're going to have an an OP. What could HP and OP mean? Look here. Blood is a fluid, correct? A fluid pressure can be described as a hydrostatic pressure. So that's what HP is, fluid pressure. Solutes suck. That moves water, that's called osmosis. So the OP is osmotic pressure. That is due to solute sucking. Therefore, we have the blood pushing out of the capillary. That's called the hydrostatic pressure of the capillary. And I want to go back to this, and I want to do it on there, so I'm going to do it down here somewhere. I don't want to erase that one. Blood, fluid, pushing out is called HPC. The solute here, sucking in, is called the osmotic pressure of the capillary. Okay, now this whole side, let's pretend this right here is just this 1/2. Okay, cutting it down the middle. I'm going to do all 4 forces, so this is cut down the middle right here, so you can see where that is. Then we have solute out here, which is a force pulling out. That is called your OPIF. And we have your fluid out here tending to push in. That is called your OP. That is called your HPIF. So there are your 4 forces. 2 hydrostatic pressures, fluid. 2 osmotic pressures, solutes, sucking. All we have to do is add up those and see whether more are pushing out or more pushing in. So let's look back to here and look what you see right here. Your net hydrostatic versus your net osmotic pressures. So I will tell you, and we know this, there is one number that we have memorized. That is this number right here. What is the blood pressure entering a capillary? 35. You guys see that? So since they are telling us that this other hydrostatic pressure is 0, what is the other hydrostatic pressure on this side called? The hydrostatic pressure of the what? See, this one's the blood, the capillary hydrostatic. So what's this one? Yeah, be bold though. Of the fluid, what fluid? Interstitial fluid. So I like to have you look back here. Here's the formula. Okay? The net filtration pressure, and you might want to write this down, is the hydrostatic pressure of the capillary, HPC, minus the hydrostatic pressure of the interstitial fluid. Okay, these are both the hydrostatic pressures. And what are we going to do? We're going to subtract the osmotic pressures. We're going to start with the capillary, OP, and we're going to subtract the OPIF. So get that down. Then we're going to go back. First, we're going to stop here. So what is this osmotic pressure? Osmotic pressure of what? Osmotic pressure of the capillary minus the osmotic pressure of the interstitial fluid. So notice how it goes capillary, interstitial, hydro, osmotic, osmotic. So we do the 2 hydrostatics first. Then we do, so we've got the hydrostatic pressure of the capillary minus the hydrostatic pressure of what? Good, you're following, of the interstitial fluid. That is 35 minus what? They're saying it's 0. Why are they saying, does anybody have a concept why this fluid pressure is 0? I'll tell you. I think, nope, the one person that listened to the lymphatic lecture might know. Here's why. Because lymphatics drain tissue fluid. They are a backward area for interstitial fluid to drain in. So when there's pressure here, it builds up, it opens up these little valves, and the fluid moves in there. So it keeps the pressure low in the tissues because there's a little back channel that the fluid flows out of, okay? So the pressure's low. Then we have the osmotic pressure of the capillary minus the osmotic pressure of the interstitial fluid. Hey, what's the osmotic pressure of the capillary, are they saying? 26. Are they? What are they saying the osmotic pressure of the interstitial fluid is? 1. Wow. So what are they telling us about the solutes out here? There's nowhere near as much as there is in the blood. There's a whole lot more solutes in the blood. Hey, there's protein in the blood. There's not protein out here. That's the major difference. So the blood's going to be more. So look, we have these. Hydrostatic pressure. Wow. That's an outward, isn't it? Isn't the HPC this right here? Okay. And this inward pressure right here, the hydrostatic pressure of the interstitial fluid, it's 0. So we have 35 moving which way? Out. And look what we're going to subtract from it. This is in with 26. And what is, so that's the solute right here, the OPC. And what's this? The OPIF, which is 1. So there's a greater inward than there is outward. So this actually becomes how much going in? 25 going in. So that means that there is 10 more, and pressure, millimeters of mercury, is what it's measured in, even though I'm not writing that. There's 10 more millimeters of mercury moving which way? Out. Right here. So the net movement, don't lose sight of the big picture. On this side, the net movement is out. On this side, which way is it going to be? In. Now watch this. I'm going to do an easy version. Of all 4 of those numbers, the only one that changes on this side is the blood pressure, which is the very first number right here. So on this side, it would be 17 minus 0 minus 26 minus 1. These are inward. These are outward. 17 out, 25 in. That's 8 greater going in. So on this side, when we look at all 4 of those forces, the only one that changed is the blood pressure. That number right there. And that allows fluid to move back in because the blood pressure is low. If the blood pressure did not drop, fluid would not move back in because everything else would stay the same. So I may ask you, when we do this, what are the 4 factors that determine whether fluid can move into or out of a capillary? What are the 4 factors? Don't abbreviate. Hydrostatic pressure of what 2 objects? Capillary and interstitial fluid. And osmotic pressure of both capillary and interstitial fluid. See, when you get into it, it gets a little confusing, but you come back out of it and you go, hey, wait, there's only 4. There's only 4 things. 2 of them are capillary. 2 of them are interstitial. 2 of them are fluid pressure, hydrostatic, and 2 of them are solute sucking, osmotic. So you put all 4 of those together and you get it. Then I want you to know the big picture, which is the only one that changes across the capillary. Blood pressure, which is called in this formula hydrostatic pressure of the capillary. The drop in pressure across there is what allows fluid to move back in. I don't usually ask all those other numbers. Okay, I want you to read about shock in the book. Shock when we say somebody has gone into shock, all it really means is there's not enough blood in the vessels. Blood vessels are inadequately filled, and blood cannot circulate normally. So therefore, your blood flow can't meet your tissue needs. But this is because your blood vessels are not full. Now notice, it could be because you lost blood. It could be because your blood vessels dilated. And there are lots of conditions that do this. And when you're in nursing school, if that's the program you go to, or if you go to PA school, man, you're going to talk about all different kinds, and they give them different names in different places as well. So I'm just introducing this concept. I want you to understand that you will go much deeper later on, and this is very important in medicine. Hypovolemic means low volume. That's from blood loss. Trauma causes you to bleed. You can go into hypovolemic shock. You see that when people have car accidents. Vascular shock, from extreme vasodilation. Cardiogenic shock, when the heart's not strong enough as a pump to pump out into the vessels. So then they give you some pictures to try to help you visualize that. And we already know about systemic and pulmonary circulations, don't we? Cardiogenic. So I'll leave you with that. We have now finished 19. I think, wow, that's enough for one night.